Our assignment was to explore and analyze a real-world dataset utilizing machine learning techniques in an open-ended fashion. Our dataset focused on soil health, including scales of key soil features, a chemical analysis, and a texture analysis. We chose to develop a model that will be able to predict health qualities of the soil, selecting soil nutrients as our outcome variable due to high levels of correlation in the data. Texture and chemical analysis variables were included in our models, and all models utilized a train, validation, and test split for the data at a ratio of 80, 10, and 10%, which was kept consistent across models. We began exploring our data utilizing ridge and lasso regression, which include a penalty term to prevent overfitting the model. These models both found poor performance with R-squared values below 50% on all data subsets. Learning curves were created and a non-penalized model was run, which identified that these models underfit quite badly and were unlikely to be improved beyond this point. As such, both the ridge and lasso models were refitted as binary classification models. The nutrient data was thus split into categories with a value boundary of 26, which was the median point. These classification models were then evaluated via accuracy, with both performing much better than their regression counterparts at 84%.
A neural network was applied to predict the levels of nutrients as previously defined. The hyperparameters chosen to optimize this model were the number of hidden layers, the regularization strength, and the loading weight. The optimal value for these parameters were chosen based on what value will produce the highest validation score and have the least likely chance for the model to overfit. This resultantly indicated to 50 hidden layers, a regularization strength of around 0.075, and a loading weight of 0.03. This resulted in a test score of 87%, with recall and precision being 88%.
A k-nearest neighbors model was constructed and optimized using both the validation dataset to find the optimal k-value, as well as using principal component analysis. The optimal k-value was found to be 23, and PCI identified that 96.52% of the data was explained by only the first 5 components. These optimization processes ensure that the model is not overfit and allows the model to better perform on unseen datasets, rather than optimizing it purely for the testing data subset. This optimization resulted in an overall precision of 91%, recall of 74%, and accuracy of 80%. Multi-class classification was considered in the creation of the model. However, adding additional classes significantly reduced model performance. This was reinforced in the SVM model, which demonstrated a similar decrease in performance when applied to multi-class classification.
A soft margin of 1 was found to be optimal for the support vector machine models to reduce overfitting and produce high validation and testing accuracies. Across the different kernels utilized, linear SVC produced the most accurate results for the binary classification. An increase in the number of classes had a negative impact on the SVM results. Hence, this was in line with the findings from other classification models explored in which binary classification was preferred over separating the data into 3 or more classes. Interestingly, increasing the number of dependent variables did not impact the model accuracies as much. This suggests that our approach to testing the variables before applying classification was appropriate for this data. Overall, the best binary classification SVM model, with a soft margin of 1, yielded an accuracy rate of 87%, precision rate of 91%, and recall rate of 84%. The neural network model produced the highest accuracy and best balance of precision and recall, making it the most preferred model of those explored for our data.